welcome to DCBA. And today I'm going to solve this problem that I had solved previously with moment distribution method. And this is type 1 problem. If you've not seen that video, the link would be given in the description, where we have analyzed this beam with moment distribution method. And now I'm going to construct the shear force diagram and bending moment diagram. Friends, this video is made due to request of many people. They wanted to see how the shear force diagram and bending moment diagram is constructed for an indeterminate beam. So let's get started. These are the values that we got from the moment distribution analysis, and shear force diagram and bending moment diagram would be constructed here. But before constructing shear force diagram, the first step that has to be followed is that we need to get reactions at every point. So here we have four supports, two fixed and two roller supports, intermediate roller supports, and we need to get reactions at all these points. So for that, we'll solve all the three segments separately, that is AB, BC and CD. So let's start with AB. We'll designate the reaction as VA and VB, and we'll start a normal summation of Fy, that is our equilibrium condition, summation Fy equal to 0. So VA plus VB equal to 80, straightforward. Summation MA equal to 0. So I'll be writing the bending moment equation here, that is VB into 3 minus 52.91. If you see that, then the minus 18.0165, I've written it as plus 18.0165, and I've shown the direction as anti-clockwise. So if you know my notations and my sign convention, then anti-clockwise moment I have taken as negative while analyzing the beam in MDM, and hence the final answers that I got, whatever answers I got in negative were my anti-clockwise moments. So minus 18.0165 kilonewton meter means this 18.0165 kilonewton meter but anti-clockwise. So I have written all the directions of the moments as per my sign convention, and I have not used the negative sign. Okay, so you are writing the bending moment equation VB into 3, perpendicular distance 3, minus 52.91 minus 80 into 1 plus 18.0165 equal to 0. We get VB equal to 38.3 kilonewton, and hence we get VA equal to 41.7 kilonewton. Okay, now we'll analyze this segment BC. Again, taking our equilibrium condition, summation Fi equal to 0, VB plus VC equal to 50 into 4, since this is a UDL spanning 4 meter length. Summation MB equal to 0, we get VC into 4 minus 41.402 minus 50 into 4 into 4 by 2 plus 52.91 equal to 0. We get VC equal to 97.123 kilonewtons and VB equal to 102.877 kilonewton. Then we'll analyze this CD. Again, our equilibrium conditions, VC plus VD equal to 40, summation MC equal to 0. So VD into 4 minus 9.303 minus 40 into 2 plus 41.402 equal to 0. I get VD equal to 11.97525 kilonewton and VC equal to 28.0248 kilonewton. Now if you see, I have these two values for VB, again here two values for VC, because B I have this point B I have in both the segments here, it is a common point, and this C is a common point in these two segments. Hence we need to add these reactions, both are VB, and we need to add them up, or we have to sum it up. So if I sum these up, I get VB equal to 141.177 kilonewton, and if I sum these up, I get VC equal to 125.1478 kilonewton. So again, drawing the beam, and as now you can see, we have all the reactions here with us, including the moments and the vertical reactions and all the supports. Okay, and this is what we require to construct our shear force diagram. Now let's get started with shear force diagram. This is the sign convention that we'll be following for drawing shear force diagram. That is, we'll be considering a section, and then we'll be summing up either the left part of the beam to that section, or we'll be summing up either the right part of the beam to that section. And when we sum up the left part of the beam, all the upward forces on the left part of the beam will be considered as positive, and if there is a downward force on the left part of the beam, it will be considered as a negative force. Again, all the forces to the right part of the beam, that is if I am considering the right part of the beam to this section, all the downward forces would be considered as positive and all the upward forces would be considered as negative. So this is the sign convention that you need to follow. Let's get started with SFT. Taking section under A, this is our first point, so we'll start from here and I'm taking the section here. So force just to the left of the section. Now just to the left of this section is basically outside the beam and there is no force outside the beam, so it is 0, it is equal to 0. And force just to the right of the section, you see this section, I'll be considering the left part of the beam, and as you can see from the sign conventions, upward force in the left part of the beam is considered as positive. So this is upward force in the left part of the beam, left to the section, and hence it is a positive shear force, and we write it as plus 41.7 kilonewton, and we plot it. So we plot plus 41.7 here underneath A. Next we take a section under 80 kilonewton force. You have to take sections under point loads at all the supports and where a UDL starts and it ends. Okay, so at all these sections you need to consider your shear force. So after point A, the next point is under this 80 kilonewton force, and taking section just to the left and considering the beam, left part of the beam to this section. So again there is no force other than this force, so it is plus 41.7 because it is a upward force and there is no other force onto the left part of the beam. So again plus 41.7 will be plotting here, plus 41.7. Now taking force just to the right of this section and considering the left part of the beam again, now we have plus 41.7 an upward force and also this 80 kilonewton included within this section. Okay, so the equation will be plus 41.7 minus 80, minus because it is a downward force, I'm sorry, yeah, minus because it is a downward force, and any force to the left part of the section going down is considered as negative. And when we solve this equation we get minus 38.3. So our shear force is minus 38.3 and we plot it here. So it goes down. Okay, the upward parts, upper part to this line is positive and the downward parts is negative. So we plot minus 38.3. Now our next point is the support B. So taking section under B and again taking section just to the left of B, considering the left part of the beam again, there is only these two forces, no other force in between. Moments are not considered in shear force diagrams because it does not have any impact on shear force diagram. Hence they are not included. But there is no other force other than these two forces. So our shear force will remain same, that is minus 38.3, and we'll plot it. Then taking force just to the right of the section, and when we consider the left part of the beam, we have now this force included in our left part of the beam, and hence the equation becomes minus 38.3, of course, adding these two, plus 141.177 because it is acting upwards, and we get 102.877. So we get a positive shear force 102.877. Then we consider our section just under C, taking section just to the left of it and considering the left part of the beam. The equation will be plus 41.7 minus 80 plus 144.177 and minus 50 into 4 because this force will be included here and it is acting downwards, this UDL, and it is minus 50 into 4, so it gives me 97.123 kilonewton negative. So we'll plot a negative minus 97.123 and then taking section just to the right and again considering the left part, the entire left part of the beam, it is minus 97.123 plus this force because it is included in the left part of the beam now, hence it is plus 25.1478, which gives me plus 28.0248, and we'll plot it. It is a positive shear force, so we'll plot it plus 28.0248. Now taking our section under 40 kilonewton load, force just to the left of this section Now I won't be considering the left part of the beam because it is too complicated to, it is, I would say, too complicated, but much exhaustive to calculate all these forces, sum all these forces up. So the much easier way is to take the right part of the section. You could have taken the right part of the section anywhere, right? Starting from right here, you could have taken the right part of the section. Whichever is easier for you, you consider that way. So, okay. So when I reach here, the right part of the section seems to be much easier because there are only two forces, but the left part has many other forces. So I'm considering the right part of the section, and as you can see, the sign convention for the right part is downward forces are positive and upward forces are negative. So minus 11.975 because it is going up, and plus 40 which gives me plus 28.0248. This is my shear force. Now taking section just to the right of this force, again considering the right part of the beam, as there is only one force which is going upwards, hence it says that upward force in the right part of the beam is negative. So my shear force is minus 11.975 and I plot it as minus 11.975. Then taking section under D and taking a section just to the right left of D, we'll be considering the right part of the beam as there is only one force which is upwards, so it is minus 11.975, and taking section just to the right of it, it goes basically outside the beam and hence there is no force there, therefore it is equal to 0, and we plot 0 as well. This is my shear force diagram for this particular problem. Now I'll be drawing our bending moment diagrams. You can draw the bending moment diagram for each segment separately, that is segment AB, BC and CD separately, because you have everything that is required here, that is you have all the moments, all the reactions as well. So you can draw the bending moment separately, or you can draw it combined, whichever suits you. But that is a bit more a lengthy method. What I'll be showing you here is a shortcut method, or a method that is very easy to understand, or a method that is very easy to apply and also is less time consuming. So before that, I'd like to explain you one thing. Consider this segment AB, and here I've shown two moments. One is going anti-clockwise and one is the other one also going anti-clockwise, but on the other end of the beam. This has a magnitude of 18.0165 and this has a magnitude of 52.91. Now what happens is, if the rotation of this moment, because of the rotation of this moment, this end goes downwards. Okay, this is basically called as a hogging shape. So if my beam end hogs, or it goes downwards, or you can also see it as a frowning face, okay, a sad face, then I'll have to plot this particular moment below this line. Okay, if my end goes downwards, then I'll have to plot this moment below this line, 18.0165. And if this particular moment takes my end upwards because of the rotation of this moment, as you can see it is going this way, so it is going to take my beam upwards. This is also called as a sagging shape or a smiley face, as you can see. So if my end goes up, I'll have to plot it above this line, so plus 52.91, and then I'll have to join them. Okay, this is one concept that you require to draw the bending moment diagrams. So let's get started with that concept. As you can see here, it is an anti-clockwise movement and it is going to take my beam downwards. At this end, it is going to frown my beam, or it is going to hog my beam. So I'll have to construct it downwards, 18.0165. Again, this movement is clockwise, and again this will try to take my beam downwards. When it gets rotated like this in a clockwise manner, it will take my end downwards. So again I have to plot it below 52.91. This will also cause a hogging shape, 52.91. So I've already plotted 52.91 here, and the check is that basically these two have to be a one line only, because both are opposite in nature, and both will have a similar impact on the beam. So both are causing it to go downwards. Okay, then the moment at this point will also try to cause it hogging shape here, and again it will go down 41.402. Then again, because of this moment, it is going to cause a Hawking effect. So again, I'll have to plot it downwards. Then because of this, again a Hawking effect. So I'll have to plot it down. So these lines have been plotted down, and then we'll have to join them. Okay. Now the next step is very important. All the segments, that is segment AB, segment BC and segment CD, you will have to consider them simply supported and find moment at every for every segment. Okay, by considering the segment AB as simply supported and a point load acting at a distance of 1 meter, you might be knowing that the moment is given as WAB by L. It is equal to WAB by L, and this is how we join it. So if I substitute this, then I get 80 into 1 into 2 by 3, that is A into B, and L is 3. I get it is equal to 53.333 kilonewton meter. Now this 53.333 is not your final moment value. Okay, this value is basically from this line, starts from this line. So but what I need is, I need only this ordinate, this much ordinate. So how can I find that ordinate? So I'll have to subtract this much value from the whole thing, that is 53.333. I'll have to subtract this much value. And how to find this value? It is a trapezoid, as you can see here, it is a trapezoid. So from linear interpolation you can find this value. It is not very much difficult. You can find it either from similar triangles. You can draw this as a triangle and find this value and then add this much value, and you can find the ordinate here. And I found it to be 29.648, and then this value we can get as actual moment is equal to 53.333 minus 29.648. It is equal to 23.686. This is my actual moment value, 23.686. Now we'll consider segment BC, simply supported here, and we have to find the moment at this point, because wherever my shear force becomes 0, my moment is maximum there. Okay, so I found this distance from similar triangles, and I found it to be 2.048 meters. It is just more than the center line of this segment. That is, the center line would have been at 2 meters, but this is the 2.058. So we'll find the moment at 2.058. How to find moment for simply supported beam? It is 100 into 2.058 minus 50 into 2.058 square by 2, which will give me equal to 99.9159 kilonewton meters. So we'll plot 99.9159 here, and again this value is this whole thing right from this line, and we require this ordinate, so we'll have to subtract this much value. And this value again from linear interpolation I get it as 46.989, and actual moment value is 99.9159 minus 46.989, we get it as 52.9268. This is my actual moment value. Okay, now the last segment, segment CD, again it has a point load, a single point load, and the moment for single point load for simply supported beam is given as WAB by L, and we get it as 40 kilonewton meter. Again this value has an ordinate from the line joining these points, so we'll have to subtract this ordinate from there, which I get as 25.3525. Thus actual moment is 40 minus 25.3525 is equal to 14.6475, and this is my bending moment diagram, final bending moment diagram for this particular sum. So I hope you got this. This is a shortcut method. You can also use the elaborate method, that is finding for each segment separately, but it is more laborious and more time consuming, so I prefer this method much more. Okay, and as you progress in your civil engineering, you will have to use this method ultimately, because you cannot waste your time finding bending moment at each point every time. Thank you so much for watching this video. Kindly share, like and subscribe. Please click the bell notification icon for more such videos. Thank you.